Hello, everyone. Welcome to today's PCI-SIG webinar, Ensuring PCI Express Signal Integrity for AI ML Architectures. We'll get started here in just a moment. Hello, everyone. Thank you again for joining today's PCI-SIG webinar, Ensuring PCI Express Signal Integrity for AI ML Architectures. I'm going to take a moment here to introduce today's presenters. We have Christopher Blackburn, Director of Field Application Engineering for Astera Labs, Matt Burns, Global Director, Technical Marketing for Samtec, and Madhumita Sanyal, Senior Manager, Technical Product Management at Synopsys. Before we begin, just wanted to remind everyone, if you have any questions during the webinar, to please enter those into the chat, and we will address them at the end of the webinar. I wanted to go ahead and pass it over to Madhumita to kick off today's agenda.
Hello, everyone. Welcome to the PCI-SIG webinar. So today we will dive into this agenda items. So we'll go over the signal integrity aspect. We'll go over different channel topologies, insertion loss, signal integrity considerations, impact from crosstalk on various AI architectures with many PCIe PAM4 lanes. And we'll see how we can forecast the system performance of such an AI architecture use case. And then my co-presenter will go over different PCIe use cases in AI architectures, block diagrams, and system topologies, PCI channels using the internal cabling and an example channel budget, and also the external cabling with retimers to extend the reach, and of course, different case studies with PCIe channels in the edge AI architecture. So without waiting, we'll get into the details. So why is signal integrity challenging for PCI 6 or 7 specifications? So as we all know, it's emerging data intensive technologies like artificial intelligence and machine learning needs to scale efficiently to process the data and run the algorithms, move the data at exponential speed from one CPU to accelerators and then out to the network, and meet the data processing demands. This definitely pushes for developing faster data standards and electrical reaches getting longer inside the tray, inside the compute tray, and of course outside the rack as well, with either electrical or optical interconnectivity. Faster data rates basically, decrease the latency, increase processing speeds in the data center servers, but complex physics challenges exist when defining these faster data protocols. At the physical layer, signals running through electrical channels like PCB traces, server interconnects, they start to hit a bandwidth limit at even 32 gig, which is PCI 5 speed. The faster a signal transmits through a channel, the more it gets affected by signal integrity issues, which limit the channel's bandwidth, distorting the channel with noise, jitter, and other impairments that makes the channel more susceptible, and more difficult for the receiver to interpret. The channel insertion loss becomes too high at this frequency to maintain a recoverable bit error rate. For example, the only way to transition from let's say 1 terabyte with 16 lanes of PCI Gen 6 to 2 terabyte was to increase the number of PCI Gen 6 channels from 16 lanes to 32 lanes. But this would be physically unwieldy and expensive to implement for every server and port in a data center. Hence, we needed PCI Gen 7 with 128 Gbps, which basically again requires PAM4. Now, what is PAM4? PAM4 is a four-level pulse amplitude modulated signal, which can be electrical or optical. Traditionally, digital signals are encoded for transmission in two levels, 0 and 1. Previous generations of serial data standards used non-return to zero encoding, rendering bits distinct high and low voltage signals with little transition times between them. So PAM4 encodes data across multiple voltage levels, four levels for PAM4, and a PAM4 signal can appear as one of four voltages during each clock cycle, each voltage level representing two bits of data rather than a single bit, right? Like you had in energy coded signal. So although you get twice as much data capacity as you can see with PAM4 in PCI Gen 7, without increasing the transmitter speed or losing the signal to insertion loss, there's a lot of signal integrity challenges associated with this. As you can see with the three data eyes within transmit swing, you are basically losing 9.5 dB, where even the inner and outer eyes are not symmetric. More transitions leads to increased horizontal closure due to inter-symbol interference with as little as 4.5 dB loss, which in energy case was 10 dB. So you launch a signal at 1 volt, it goes through a, let's say, 35 dB channel, and the signal left is close to 6 millivolt, let's say. So a lot of, you are losing the signal quality on the way through the channel. So for example, for long reach channels, for 33 to 37 dB, which we will be discussing in the next couple of slides, definitely need higher equalization on the SerDes side. Longer channel, higher speeds, this increases the intersymbol interference, especially the precursor ISI. And PAM4 further it's basically deteriorates the ISI issue. And the ISI becomes a larger percentage of the inner eye opening. So, we had the analog FFE-DFE approach till the 32 gig PCI Gen 5, but limited in speed equalization. Hence, you needed a further advanced ADC DSP based architecture on the PHY side. Okay, um, so let's look deeper into the channel topologies in context of AI ML architecture. For example, there could be chip-to-chip connectivity. As you can see here, it's a kind of shorter channel between a CPU and GPU link within a compute tray. And on the left-hand side, the top left picture shows a connectivity with a mezzanine connector. So basically, the channel traverses through the CPU package, through the backplane, through a mezzanine connector to maybe another tray to a GPU. Then on the other side, on the bottom side, if you look at the even the more stringent channels where there are multiple connectors and multiple trays or backplanes, so there could be a riser card or add-in card in the channel path where your channel basically traverses through the CPU package, backplane, orthogonal connectors, rise-in cards, edge connectors to the add-in cards to the GPU package and to the GPU. Or you can have multiple backplanes with more than two connectors. So all these basically adding to the uh, the channel characteristics and making it worse for in terms of the signal integrity aspects to it. You have more discontinuity now, which even can cause reflection and so on and so forth. So basically, these kind of channels, and this is something that we are talking about within the compute tray, and you can even expect that the PCIe to extend beyond the tray, beyond the rack, and that would be through, of course, through copper cable or even optical cables, right? So this is extremely challenging if we talk about in perspective of AI ML architectures. So now, if we look at the specifics of the PCI Gen 6 or Gen 7 channel consideration or channel length, we can see that, going from Gen 5 to Gen 6 to Gen 7, of course, the Nyquist changes, and from Gen 6 to Gen 7, the root complex package itself, you can think of about like 256 lanes in the package, but the package loss still needs to be within the range of 9 dB for root complex. And CIM connector did not change much. Add-in card, okay, 1 dB extra for, of course, then again, you have the budget for the baseboard, which can be backplane or different kind of rise-in cards, add-in cards, or could be a copper cable or so on, right? So this seems to be kind of challenging in terms of signal integrity aspect to it, and you are limited to have almost 13-inch of baseboard routing and 4-inch of AIC routing. So more expensive PCV material and board and substrate material is needed for the same channel, from moving from Gen 6 all the way twice the speed to Gen 7. So now we have looked at different kinds of channel topologies. So now, even going before going to take a look at the silicon performance, the system implementers need to forecast the channel performance by looking at different aspect of basically evaluating the SerDes bit error rate, which is the key metrics for the overall system performance. And we have seen the, in traditional signal integrity simulation with using the golden circuit based analysis, it basically is extremely slow. It cannot handle complexities in terms of jitter analysis, crosstalk, and data patterns. And of course, the system implementers who might not have the proper SerDes knowledge need to, go through the whole exercise of knowing the SerDes, how to tune it in terms of the circuits simulation perspective. Hence, the still in Gen 7, the solution is IBCMI model, and and use the IBCMI simulation to calculate the overall performance of the end-to-end link. So you can create the end-to-end link with your SerDes TX MI model and use these parameters of the channel, and also use the SerDes receiver AMI model. And you would need to look at the eye height, eye width, and other figures of merit in order to evaluate the end-to-end channel performance. So your TX and RX IBCMI model would have the nonlinearities, jitter and noise, and TX model should have the fine-tuning capability of the TX equalization control. RX, of course, will have to model the analog front end and the whole DSP. And yes, some EDA tools can process the executables on the receiver side and perform extrapolation and give you a statistical content. So in all, so IBCMI modeling is definitely a must-have to in order to kind of perform the end-to-end simulation of the link in a AI ML use case, and of course ensure interoperability and accuracy and efficiency of the system performance. So next we look at a specific case study on a AI ML architecture, which consists of many PCI Gen 6 or Gen 7 lanes. So here in the farther left, we are looking at a full chip. For example, it could be a switch or an accelerator chip where you have many lanes of SerDes and as well as many PCIe 6 or 7 controllers. Because the link might support either 4, 8, or 16 link width, and hence you would need multiple controllers, and you would need to basically replicate the same on all edges of the die. What it means for the overall system performance is you now are not looking at only couple of lanes, but in context of hundreds of lanes in a AI ML architecture, which means that it will affect your system performance in silicon, and you would need to forecast that and get and possibly use further intensive look at the simulation aspect much before you move into the tape out or in post silicon phase. So basically you would have a larger package size, and you would need to look at different kind of routing for TX and RX, and perform high frequency structural simulation. And that would mean basically you would analyze different reflection, coupling, and attenuation effect, and that basically would give you the multi-physics solution, and hence you would basically evaluate the crosstalk with different simultaneously switching lanes in context of AI/ML architecture. And that needs to definitely meet the specification in terms of insertion loss, in terms of return loss, near end crosstalk, far end crosstalk, and that definitely would give you the sign off criteria for a overall system performance in context of many PCIe switch or accelerator use case. And now my co-presenter will dive into the details of different cabling technology or topologies here. Thank you.
Thanks, Madhavita. Yeah, so Madhavita did a great job of explaining some of the signal integrity challenges in these architectures, and we talked a little bit about some of the cable topologies. I want to focus on a few different topologies here. So if you look to the right, there's 4 channels that we'll talk through. 2 of those are GPU to GPU connectivity, where we're clustering GPUs together through I/O cables on the front of the rack or through a cable backplane on the rear of the rack. And then we'll look at GPU to CPU connectivity, whether that CPU is in an external head node, the different rack elevation connected with an I/O cable, or whether that CPU is internal to the JBOG or just a bunch of GPUs in the same chassis and connected with an internal cable. As we look at the challenges from PCIe 5 to 6 to 7, system architectures are definitely changing, and there's a lot more cables being used. In addition, high performance PCB materials continue to be used. And when you add these two and you consider the challenges for PCIe 6.0 and 7.0, for some of these channel topologies, it's still not enough. And that's where retimers become vital to making these system architectures possible, especially when we leave a chassis and start looking at external cabling. So with that, I'll dive into each of these channels, and we'll talk through some insertion loss budgeting and some considerations of these channels. So the first channel we'll walk through is connecting GPUs together through an external I/O copper cable. If we look to the left, we have GPUs that sit on a mezzanine card with about 2 inches of trace on the mezzanine card through the mezzanine connector and into the baseboard, and then about 10 inches of trace on the baseboard. That is replicated on the other baseboard and system. And then those 2 systems will be connected through a passive copper cable or a DAC. In this case, we show an OSFP XG connector and cable, but this could be other form factors like QSFP-DD or CDFP. And in this particular channel, I show a 1.5 meter cable at 28 gauge. And if we step through the insertion loss budgeting to get from GPU to GPU through that cable at 16 gigahertz for PCIe 6.0, we're right around 40 dB. And at 7.0, almost upwards of 60, 61 dB. right? So it's very clear that we're running out of gas when we get to the faceplate, and that these external cabling topologies are going to be very difficult without the use of retimers or optics. So when we take a look at that same channel and you focus on the right-hand side of the screen, we've now replaced that passive DAC with an AEC. And if you look down at the insertion loss budgets, there's the different segment totals. So segment 1 is from GPU to the I/O connector. Segment 2 is the the AEC, the active electrical cable, and segment 3 is from that connector to the other GPU. And when we look at using an active electrical cable with retimers on both ends of the cable, we're able to get well within the channel budget constraints for PCIe 6.0 and 7.0. So if you look at segment 2, that's the highest contributor with 22 dB, well under the 32 dB limit for PCIe 6, and 35.3, under the 37 dB limit for PCIe 7. One other thing to pay attention to is in the passive DAC scenario, the estimation was done at 1.5 meters. On the active electrical cable, if you look, we were able to get 3 meters of reach because we're retimed on either end of that cable. And in addition, we were able to change from a 28 gauge, large diameter wire gauge to a finer gauge, 32 gauge, which helps with the cable routing and rack management. In a typical GPU cluster, there's going to be hundreds of these cables, and the finer gauge certainly helps with the mechanical cable routing. In addition to the longer length, when we look at clustering these GPUs in a scale-up architecture from a single rack to now enabling reaches that can span multiple racks, you can increase the size of that scale-up cluster. So now let's take a look at a similar topology, but through a copper cable backplane. If you look at the left-hand side, we're showing a passive copper cable backplane, and similar trace lengths and topology on the baseboard, but instead of routing to the front I/O, we have about 6 inches of trace on the baseboard from the mezzanine card to the backplane connector, a 28 gauge 1.5 meter backplane cable, and same JBOG on the other end. And when we look at the insertion loss accounting here, at 16 gigahertz, we're right on the limit of the 32 dB limit for PCIe 6 and well above the limit at PCIe 7. So similar story as the previous slide when we looked at the external I/O cabling. If we look at placing retimers in between that GPU mezzanine card and the backplane connector, we can start to isolate and balance the channel into 3 segments that can meet the channel budget. This looks very similar to the previous slide. And again, if we look at segment 2, the highest contributor is that cable link, and we're well within the PCIe 6 and 7 budgets. And we were also able to increase the cable length and move to a finer gauge. Similar story when we think about backplane cabling. We're typically spanning a single rack, so 2.3 meters is sufficient to span from, say, top third to bottom third of the rack. And then the number of connections connecting these JBOGs together is constantly increasing, and leveraging solutions that use a finer gauge cable and higher density backplane connectors can enable these cable backplane topologies to be possible with those large lane counts. So now we'll dive into some CPU to GPU connectivity. The first case here is with an external head node where the host processor will sit in a separate rack elevation than the JBOG. We have the same baseboard topology as we looked at in the first channel, a 28 gauge 1.5 meter passive DAC, and then about 8 inches of trace from that I/O connector to the CPU. Again, similar story at 16 gigahertz and 32 gigahertz, we're well above the budgets. So when we look at adding an active electrical cable to the channel, we are able to essentially double the length and move again to a 32 gauge with similar segment totals coming in well under the PCIe 6 and 7 budgets. One of the considerations when we think about active electrical cables, typically they have the retimer on both ends. There will be some cases where if the channel is lopsided, you are able to implement what we'll call a half active electrical cable, where that retimer sits on one end or the other and can balance the channel if you don't necessarily need all of the reach, or in a case where you have maybe flyover cables or other technologies inside one of the chassis. So with that, we'll look at an internal cabling example. This would be a case where we would have a CPU and GPU in the same chassis. Typically, one of the trends we're seeing is that the chassis themselves and the racks are getting wider and deeper and growing in size to accommodate the AI and ML architectures. That could also be multiple rack units high in a certain chassis, where the CPU could sit 2 or 3 rack units below the accelerators or above the accelerators. And when we think about some of the internal cables, the length of those cables is increasing. So even if we have short traces from the GPU or the CPU, we're routing internal cables in these systems typically to the sides of the chassis, down through the length of the chassis, and then vertically up to the different boards. And some of these cable reaches internally can be approaching lengths greater than 1 meter. So in this case, we have a GPU to a near chip copper cable with about 2 inches of trace, a 30 gauge 1.2 meter cable, and then on the other side, on the CPU side, about 6 inches of trace from that near chip copper cable to the CPU. And here's a case where at PCIe Gen 5 at 16 gigahertz, we're well within the budget to use a passive cable. But when we think about PCIe 7.0 channel, this is where things get a little bit more difficult, and we are out of budget given the increase in some of the insertion loss due to the cable, the traces, and the packages. So in the case to the right, we show implementing a retimer, whether that's integrated into the internal copper cable, similar to how we do external AECs, or whether that retimer is on the PCB. That retimer can segment these channels and get them well within the budget. So if we look at segment 1, where you have a passive connection on the GPU side, that takes up at PCIe 7 about 30 dB, which keeps us well under the 37 dB budget. So now that we've looked at some of these channels, just maybe a few comments, right? And kind of back to the introduction slide of those channels. The use of copper cables is going to remain because they are cost effective and reliable. PCB materials and high performance PCB materials are, although they're getting better, it's not enough to create some of the channel topologies that system architects are looking at deploying. And retimers are going to be vital at PCIe 6.0 and 7.0, especially when we think through this GPU to GPU or GPU to CPU use case. So with that, I'm going to pass it over to my colleague Matt, and he will dive into some of the technologies and signal integrity on the edge.
Thanks, Chris. Thanks, Matamita, for the setup. Thanks again for all of our attendees listening into our webinar as well. So Matamita did a great job, setting up the SI challenges that PCI Express implementers have, making the transition from PCI 5 to PCI 6 and PCI 7 with PAM. She did a nice job of detailing the standard use cases with CEM AICs at PCI 5, PCI 6, PCI 7. And Chris obviously did a nice job, talking about AI use cases when it comes to, data center implementation, GPU to CPU linkage as well. What we're going to do for the next 10 or 15 minutes is look at how do we implement PCI 5, PCI 6 on AI at the edge, and what are some practical use cases there in terms of how OEMs and implementers are using the technology. So what we wanted to take a look at was the usage of PCI 5 and PCI 6 within the PICMIG COM-HPC ecosystem. COM-HPC stands for Computer on Module High Performance Computing. For any of you that are familiar with embedded computing, COM-Express has been the workhorse platform for embedded computing probably for the last 15 years. It's a great platform. It's not going anywhere, but it has performance limitations due to the connector designed in. The connector technology is 15, 20 years old. So there was a need for a new platform to get to higher speeds, higher performance, which we'll talk about here in just a moment. COM-HPC, open standard for embedded computing platforms. It offers server-grade performance at the edge. We're also starting to see interest in using COM-HPC for AI at the edge as well. There's a number of sizes and configurations to support various use cases, but the use case or the channel information is the same across all these configurations. We'll talk about that here in more detail in just a moment. And then COM-HPC, similar to PCI-SIG, is a very big community. There's implementers across the world and geographies around the world as well. So digging in the details just a little bit more, what were some of the technical challenges that COM-HPC tried to answer because of the limitations on COM-Express? Well, the biggest thing, or one of the biggest things, was the need for more speed and more protocols to be supported through the interface. So COM-Express is maxed out by about PCI 4 performance, 16 gigabit, as has been discussed. But there is a need to get to PCI to enable PCI 5 and future-proof to PCI 6. So what that really meant was creating an entire form factor and a new interconnect technology that would allow for faster speeds. So you can see there that when originally conceived, probably before the pandemic, the target was PCI 5. But as PCI 6 became reality, make sure that the platform was future-proof for PCI 6 technology. So that's how the working group, the technical working group within PICMIG, went to, started the efforts of how do we design a ecosystem, how do we design a form factor to enable the higher speeds that servers at the edge, AI at the edge really needs. So there's a lot of similarity between the CEM AIC form factors and some of the use cases that Chris talked about in AI that you also see at the edge. So from a PICMIG COM-HPC perspective, there's two use cases. There's what's called device down within the COM-HPC spec. You have your there's the mezzanine, which is the COM-HPC module. There's a CPU, a GPU, some other compute system. It runs to the edge of the COM module. It goes down through the mezzanine connectors down to the carrier card and then out to a corresponding chipset. Obviously, we're applying the device down use case for PCI Express. Because COM-HPC is a server-based COM module, another use case is also enabling device up, which mimics having a COM module as the CPU within your ecosystem, and then PCI Express CEM AIC expansion slots on a carrier card. So there's a little bit more transition within the signal channel going from the CPU to the mezzanine connectors to the carrier card, and then back through a CEM connector, and then up through a traditional AIC. So the question comes up is, obviously, the PICMIG technical working group knew the loss budgets that were available for these channels, But how do we take the PCI 5 loss budget? How do we take the PCI 6 loss budget and apply it to these channels? How do we assign the losses to each component within the channel so that we can still enable the performance? And obviously, you're going to have a fixed loss within the package. You're going to have a fixed loss within the connectors. So there's variability in terms of how long you can make the trace lengths, what type of PCB material you use, and the like. So how did the PICMIG COM-HPC Technical Working Group go about trying to answer these questions? Well, it really gets down to looking at the loss per component. And it's, again, using the loss budget provided by PCI-SIG for PCI 5 and PCI 6 as the working, the goal, but looking at how each of the particular components along the signal chain contribute to that loss. So you have to look at there's a new connector. The COM-HPC connectors are different from the card heads that you see within the CEM AIC. So the loss profile is going to be different. How are you going to put the breakout within that connector? It's obviously going to be different from CEM AIC. What PCB materials, what type of traces you use, how do you break out the signals from the CPU on the carrier card? Same thing down on the root complex on the carrier card, and then the endpoint down on the carrier card. So the SI team went through a component by component analysis and looked at the loss profile, both from a simulated standpoint and also from a test standpoint. So simulating it, build and solve 3D models by creating S parameters for each of the key components. That's the module PCB, the carrier PCB, the connector models, the strip line models. Simulate the components, and then build the channels out of the components that are available, and then the results were documented within the spec. So what were some of the results? This is a good example. This is just one example of some of the design challenges that the PICMIG COM-HPC Technical Working Group met when trying to implement PCI 5 on a new interconnect platform. This shows the recommended differential breakout for the 4-row connector that's used within COM-HPC. You can also see that the differential pairs are recommended to use a ground signal ground, so that there's essential grounding within the system. The spacing between the center rows of the connector were actually the first version of the connector was designed to have maximum density. But after simulating the first initial designs, we realized that there was a little bit too much crosstalk to fit the PCI 5 recommended profile. So we actually extended the distance between the rows of pins to 2.4 millimeter and 2.2 millimeter. And what that allowed for was, not only did we have improved routing in terms of how we could route the differential pairs for PCI Express, both in a north-south or east-west solution, but it allowed for increased via displacement within the system. So not only did you get the good signal routing from the pins to the vias, but you could allow for more ground vias, not only around the connectors on the pin, but up and down the spacing between the pins. So this design technique of optimizing the breakout region, optimizing the termination of the signals to vias and the like, helped to optimize the performance of the system within the COM-HPC module and the COM-HPC carrier as well. So the end result, when looking at the loss per component within the system, is documented here. And it also talks about some of the assumptions that were made trying to apply the PCI-SIG channel loss profiles to particular components within a COM-HPC channel. So, some of these numbers mimic some of the data that Matamita shared. So the module package, the loss per package, is assumed to be 9.2 at PCI 5. The routing through the PCB, 6 dB. The coupling caps and the vias, 1.8. The COM-HPC connector, 2 millimeter. The carrier routing and the carrier package is shown. So the known values that you have here are the carrier package, the module package, the vias, and the connector. And then the variability that you have within the system design is how much loss do you enable for routing the trace lengths between the CPU on the module to the connectors, and then from the connectors to the endpoint on the carrier card. So based on the SI analysis that the team went through that we detailed, this was the loss profile that the team developed. So that's great. You think, okay, we have a loss profile budget for each of the respective components on an embedded computing system for COM-HPC. But what does that mean at the channel level? How do we have confidence that the loss profile budgets that the team came up with make sense for real-world channels? So that's where taking the individual component S parameters, concatenating them together, and creating an entire channel-wide model, and then building the channels via MATLAB and then simulating the channels using CEM helps us to get a better profile. So the illustration here shows how it shows graphically how the channels were built for each of both use cases. Here, we're just looking at the device down. So the TX package is obviously the root complex. You can trace the signal from the package to the strip line, to the vias, to the caps, to the vias, to the strip line, to the connectors, the breakout regions, strip line routing, and then to the RX package, which is the root complex. So again, we create the S parameters at the model level, we create the S parameters at the channel level, build them apart, and then simulate the system from that standpoint. What that allows us to do is, while using CEM in collaboration with the channel models, we're able to come up with suggested trace lengths, both on the COM-HPC module and also the COM-HPC carrier card, based on design assumptions. The challenge that the group worked with was, this is design guidelines for an entire ecosystem. And some implementers are going to have different design criteria versus others. Some implementers will want to maximize cost effectiveness by using a standard loss PCB material, whereas other implementers may want to maximize performance, which would allow them to use a lower loss PCB material. So by coming up with a standard budget on the trace lengths on the module and also on the carrier, you can vary the trace lengths on the carrier and the module based on the dielectric material of a standard loss PCB versus something that's very low loss. And obviously, using a lower loss material is going to allow you to increase, assuming that the loss is constant at the root complex and at the endpoint, as well as in the interconnects. You have system variability, flexibility, scalability within the system design in terms of the PCB material that's chosen. So we're going to turn it back over to Kevin for any Q&A that the attendees may have.
Great. Well, thank you, Matt, Chris, and Madamita. We did have some questions coming from the audience today. And reminder to everyone to please, if you have any questions, please submit those in the chat, and we will try to get to them in the time we have. Great. So the first question we had today is regarding the impact of inner and outer data eyes not being symmetrical, and what are the impacts of this on PAM4?
Okay, I think I can take that. So with PAM4, it's eye linearity, which means compression and skew both. So the four eyes in PAM4, right, they align in time delay but vary in eye height. That's your and then the centers, that basically centers the eyes, center of the eyes that vary in their time delay. So it's both compression and the skew. So that's the impact on PAM4. Now, standard committees limit the maximum allowed compression and skew and do provide the measurement techniques. And the impact of the inner ICE on both symbol error rate and bit error rate, that basically, depends on the receiver that you would be using, the SerDes receiver, right? So let's say the receiver uses an ADC or like 3 voltage slicers set at a common time delay to differentiate between the 4 symbols, then basically you would need the mask test to check the signal compatibility. So basically that's the impact and kind of the solution and the measurement methods to make sure that you pass the asymmetry mask test for PAM4. And it's different from energy eye analysis to PAM4. Okay, thanks.
Thank you. I think this one would probably also be for you, Madamita. Is there an estimated power cost for the AECs?
Yes, so active electrical cables. So that would require a timer, which means there will be another SerDes inside the AEC. So definitely that would add to the power budget. But that being said, you need the reach, so you pay in terms of power, maybe and latency. Yeah.
Okay, great.
Thank you.
Yeah, thank you. This next question would be for Chris. I believe it's so instead of retimers, can signal integrity be solved with redrivers and still meeting the PCIe channel loss budget?
Yes, absolutely. Redrivers are another option. They will offer lower power than a retimer. One of the challenges with the redriver is that it will amplify the noise profile. So when we think about the higher frequency for PCIe 7, or we think about PAM4 modulation, redrivers will have some of their own challenges that we won't experience with retimers. So both are going to be valid options, and selection of the device will certainly depend on the channel topology.
Great. So another question here. I believe this is on the insertion loss budget. So 35.3 is quite close to 37.0. What are the assumptions on things like surface finish on the cable wiring or skin effects and the other physical properties of connectors, etc.?
Yeah, I'll take that one, and then Matt, if you want to chime in as well. So when we look at insertion loss budgeting, it's a first step when evaluating a channel, right? It's obviously not taking into the effects of crosstalk or return loss and your true eye diagram and channel performance. So when we look at whether there's, say, short traces between connectors that could amplify reflections, and we look at the variability across high volume production and whether that's on the PCB or on the cable, right? There's always going to be some variation in that channel. So there's some rules of thumb when you're evaluating insertion loss budgeting that you want to be about 10 or 15% lower than that max. Now again, that's not gospel, and that will change depending on the channel topology. So actual simulations need to be run to understand how close you can come to that overall budget limit.
Yeah, it's just a brief commentary. I'd agree with the point that Chris made. When it comes to loss budget analysis, it's a starting point. And I think that Chris showed that in his portion. And I think that we showed that, Samtec showed that in the portion when talking about COM-HPC. So, the other challenge too is there's so much variability within the system that a designer or an implementer has, and that's going to affect the performance of the system. So it's obviously PCI-SIG provides the guidelines for CEM AIC, and they're continuing to work on providing guidelines, using CopperLink and some of the cabling technology. For a PCI Express, or for PCI Express implementer, their channel may not be defined by PCI-SIG. So a lot of it's just going to be trial and error. Obviously, you're going to simulate it as best you can based on your design rules. Obviously, you're going to work with your ecosystem of support. Your PCB vendors, your connector vendors, your IC vendors. Depending on where you're at within the ecosystem. But it does require a lot of fine tuning. But thankfully, there's a lot of expertise out there, not only by what's provided through PCI-SIG, but also through the component providers along with the channel width as well, or along the signal channel as well.
Great. Thank you both. Our next question here. Assuming you are using ultra low loss material for your model for PCIe 6.0, what loss did you assume for your PCB trace in your cable examples? And then the comment, it seems like your trace loss is well below published numbers for ultra low loss materials, 0.7 dB per inch versus approximately 1 dB published for Meg 6.
Yeah, I'll take that. I think that's with respect to my channel. So we were looking at a Meg 7 or Meg 8 equivalent with some of the trace loss. I think as back to the previous question, and we're making some assumptions. I think when we look at whether it's Meg 6 or Meg 7 or Meg 8, the same assumptions and analysis holds true, where you're not going to be able to get these longer cable reaches despite what PCB material you're using. So even with a really high performance, say Meg 8 equivalent, to get these external cable channels to work, right, you need more than just an improved PCB material.
Okay, great. Our next question is, what are the etch width and air gap values for the COM-HPC connector routing you displayed?
That's a great question. I wish I had those technical details, but I don't. But if whoever submitted that question, if you want to send me an email at matthew.burns@samtec.com, I'll be happy to answer that offline.
Great, thank you, Matt. Let's see here. This is another a COM-HPC question, just general. Where is COM-HPC used today?
Good question. We see a lot of interest in some mil-aero applications, for advanced communications, phase radar array, those types of things. We're starting to see interest in humanoid robotics. We're starting to see some interest in COM-HPC within process factory automation, machine vision, and the like. So not a lot of interest in the data center per se, but where you need server grade performance within telecommunication, co-located office. So outside the data center, but still high performance embedded.
In here, what is the maximum bit error rate supported for PCIe 6.0 and PCIe 7.0?
So the spec specifies 1e-6. That's the pre-FEC bit error rate. But really what you would like to see is the post-FEC error-free link. So depending on the implementation on the SerDes side, so it could be anything better than 1e-6. Let's say across PVT, assuming you have all the crosstalks, channel impairments. So that's the worst case, and minimum bit error rate is 1e-6 as defined by the specification.
Right. So next question here. When you do your 3D electromagnetic modeling, do you merge the connector with two printed circuit boards in HFSS?
I think there's a couple ways. That's a great question. I think there's a couple ways of looking at that. You can build the models obviously within HFSS as components and then merge them and then run the simulation, or you can take the systems, or you can take the individual component models of the PCBs and the connectors and concatenate them using MATLAB. I'm not an SI specialist, but that's the approach. Really dictates familiarity or comfort level with HFSS and other simulation tools.
Thank you. Next question here. When given the option to choose a cable connector with either hole, press fit, or surface mount connections to the PCB, what has the optimal signal integrity in the PCB breakout region?
I'll take a stab at that one. Again, it's going to depend upon the interconnect chosen. Obviously, there's a lot of guidelines provided by PCI-SIG for the CEM AIC solutions. It's really going to come down to use case and performance. In general, what we're seeing with next generation interconnect, things are getting smaller, things are getting denser. So you're just, from a manufacturing process, you're going to use a surface mount interconnect more often than not. So it's all about working with your interconnect provider, working with your PCB manufacturer to make sure that you optimize the BOR to get the SI that you need. I wish I had a one-size-fits-all answer to that question, but I don't know that there is a one-size-fits-all solution, because there's, frankly, for cable connector attaching to a PCB that's able to support PCI Express technologies, there's a multitude of options on the market.
Thank you, Matt. So I think we have time for a couple more questions here. So next one, what are some of the signal integrity analysis tools that are being used to create and analyze IBIS models?
There are a couple of different tools. One of them, CEM, I think Chris mentioned about it out there. So you can basically perform the IBCMI simulation, create the model, and also perform the end-to-end simulation there.
Thank you. So our last question today is, are you also considering the use of fiber optics and optical transceivers to interconnect boards?
Yeah, I'll take a stab at that one. Absolutely. So there is a PCI-SIG workstream covering optics over PCIe. And when we think about some of the use cases about the scale-up network and GPU clustering, or even disaggregation of compute and memory resources, right? When we start to scale beyond 3 racks, that's where the reaches of an active electrical cable become challenging, even with the largest wire gauges. So there are many efforts around the industry to look at optical cabling using PCI Express.
Yeah, and I would just to, as an interconnect provider, I would 100% agree with what Chris mentioned. And that magic 7 meter to 10 meter use case, which we see especially in GPU clustering, is really driving these systems. And I'd say it's obviously it's heavily, PCI-SIG is heavily invested here, but it's an industry-wide target, and it's necessary to get the signal lengths beyond what copper, even the highest performing cabling with the best retimers. There's just physical constraints there as the data rates get faster. So yes, you'll see more optics from board to board, or even chip to chip with optics on package in the future.
Right. Well, thank you all. I think that's all the questions we have time for today. So I want to thank everyone for attending today's webinar and to our presenters for sharing their expertise. The slides from this webinar will be available soon on PCISIG.com, and an on-demand recording will be posted on PCI-SIG YouTube channel and also here on Bright Talk. Once again, thank you everyone, and have a great rest of your day.